The Chapter 5 Thermochemistry notes for AP Chemistry, and this chapter deals with energy and heat of chemical reactions. So we have the definition of energy, which is the capacity to do work, and that's the definition from a physics class. And in physics there are two main types of energy that we talk about. It's mainly kinetic energy, which has the formula 1/2 mv squared, and that's on the AP chemistry equation sheet. And we also have potential energy, which is the energy due to the position of an object, mainly due to gravity, which is calculated by taking the mass of the object times the acceleration of gravity times the height that it's off the ground. So there's two types of energy, kinetic and potential. In chemistry, we usually concern ourselves with heat energy that's gained or lost during chemical reactions. So we're not going to worry too much about kinetic and potential energy, but mostly with the energy of heat of a reaction. On the next slide, we have the units for energy that are used. The metric system unit, or the SI unit, is the joule, which is derived from multiplying the mass unit, which is a kilogram, times the velocity unit squared. So it's a kilogram meter squared per second squared, or that's known as the joule. And sometimes we use the calorie, which is a good conversion factor to know. It's 4.184 joules is exactly 1 calorie. Now a food calorie, or a nutritional calorie, is actually 1,000 chemistry calories, or 1 kilocalorie. So if you were to drink a soft drink and it says that it's a 1 calorie drink, they're actually lying to you. It's 1,000 real calories that you would calculate in a chemistry class, or it's a kilocalorie. So it's abbreviated with a capital CAL instead of a lowercase CAL. Now we have some other terms which are used a lot in this chapter, the system and the surroundings. For a thermochemical reaction, we need to define what the system is, and that's the part of the reaction that you're usually interested in. And the surroundings is everything else, which would be the rest of the universe. So the example that I have in the notes is if you're interested in a reaction between hydrogen, oxygen, and a cylinder, then the hydrogen and oxygen in the cylinder form the system, and everything else outside the cylinder would be the surroundings. Now there are two ways to transfer energy, which the next slide shows. The first way of transferring energy into or out of a system is by doing work on that system. And again, in physics class we learned that work is the force times the distance. So you apply a force to an object and it moves a certain distance, and that's called work. The other way to transfer energy in and out of a system is with heat. So energy always transfers from hot objects to cold objects, never the other way around. It always goes from hot to cold. So for instance, you can't suck the cold out of something. You can only suck the heat out of it. Energy, therefore, has a new definition. It's not only the capacity to do work, it's also the capacity to transfer heat. So we have two ways to define energy, the capacity to do work or transfer heat. And we're mainly going to concern ourselves with the transfer of heat. In physics, you would worry about the work. Now we have the definition of the first law of thermodynamics, and it basically says that energy cannot be created nor destroyed in a chemical or physical change, and it's basically a restating of the conservation of energy. So the first law is really the conservation of energy. And from our definition of system and surroundings, the energy of the system plus the surroundings has to stay the same. Thus, any energy that you transfer from a system must be transferred to the surroundings, and any energy that transfers from the surroundings must go into the system. Now we have a definition of internal energy. Internal energy is the total energy of a system. Now it turns out you cannot measure absolute internal energy. We can only really measure the change in the energy, and so we always use the symbol delta for change in. So you can always measure delta E, never the absolute internal energy of a system. So we're going to be doing change in the internal energy. And on the next slide we have when a system undergoes a physical or chemical change, the change in the internal energy is given by those two factors we discussed on the previous slide, the work that the system does and the heat that is transferred. So we have the change in the internal energy equals the heat plus the work. So any change in internal energy is given by the heat added to or absorbed by the system plus the work done on the system or the work done by the system. And on the next page we have the signs for when you're doing work on a system or work done by a system, and heat transferring in a system or transferring out of a system. So Q, which represents the heat going in a system, would be a positive value, heat coming out would be a negative value, and work done done by the surroundings on the system, so work going into the system would be positive, and work done by the system on the surroundings is a negative sign. Now we really don't need to concern ourselves too much about work because again that's a physics topic. We really need to concern ourselves with the sign convention for heat. So when heat goes in it's a positive number, when heat goes out it's a negative number. Now we have the definition of exothermic and endothermic. Endothermic processes absorb heat, so again that would be a positive value, and the reaction would feel cold. So if there's an endothermic reaction that's taking place and you grab hold of the container, the heat will transfer from your hand into the system. That's why Q is positive. So an example of that would be an instant ice pack. You crush it and it feels cold because it's taking heat from your hand and pulling it into the system. For an exothermic reaction, it would be the opposite. It transfers heat to the surroundings, so you would have a negative Q value, and that reaction would feel hot. So when you burn paper, that's an exothermic reaction because you can feel the heat that's given off. And there's a little picture of the heat going in or the heat coming out. Now they use the symbol H or delta H for endothermic and exothermic. So delta H will be positive if it's an endothermic reaction, and it will be negative if it's an exothermic reaction. Now Q and H are almost the same type of variable, and we'll discuss that on the next slide or a later slide. Now we have the definition of what's called a state function. Now a state function only depends on the initial and final conditions of a system. So an example of this would be if you are worried about the altitude difference between Denver and Chicago, it doesn't really matter if you fly or drive. You only need to concern yourselves with the elevation of the two cities. A good example, another chemistry example of this, or a good example of this using actual chemistry terms instead of just driving, would be if you wanted the internal energy of a container of water at 25 degrees Celsius if it has a mass of 50 grams. If you want the energy of that system, it doesn't matter how you got to those final conditions of 50 grams at 25 degrees Celsius. You could heat it up from 0 or you could cool it down from 100. The internal energy of that system at 25 degrees Celsius would be identical. So a state function doesn't really depend on the it doesn't depend on how you got to those conditions. On the next page we have another picture of a state function. A state function does not depend on how the internal energy is used. So if you wanted to know the energy lost by a battery, it doesn't really matter if it's just wasted by heat from a toy car, or if that energy is used to power a fan. So a battery in a flashlight can be discharged by producing heat and light, or the same battery in a toy car produces heat and work. It doesn't matter, you'd still get the same change in energy. So you could have it all heat, or you could have it heat plus work, and again we had that formula before, Q plus W equals the change in energy. So a state function only really depends on the first conditions and then the final conditions, and you're going to just basically subtract them to get the change. And this delta E value being a state function will lead to a delta H value, which is also a state function. So on the next slide we see that E is a state function, and then we're going to introduce H. And again, H is also going to be a state function. Enthalpy is the main vocabulary word of the chapter, and enthalpy stands for the heat transferred between a system and the surroundings if it's carried out under constant pressure. Now, the only reason I stress this constant pressure idea is because if it's not under constant pressure, you can call it Q. But if it's under constant pressure, like in an open container when you run a reaction, it's going to be under constant pressure, and so you can call it delta H as opposed to Q. So enthalpy is also a state function again, which means that it only depends on the initial and final conditions, and the signs are just like Q as I mentioned earlier. Delta H is positive for endothermic and it's negative for exothermic. On the next slide we're going to calculate the change in enthalpy just like you would expect. You only need to worry about the initial and final, and you subtract them. So we always take the final enthalpy minus the initial enthalpy, and that's the change in enthalpy. And for a chemical reaction, your final are called the products, your initial states are the reactants. So if you want the change in enthalpy for a reaction, or the delta H of a reaction, you just take the H's for the products minus the H's for the reactants. Now enthalpy change that accompanies a reaction is called enthalpy of reaction, and sometimes it's called the heat of reaction. I kind of like the term heat of the reaction because the letter H reminds you that it's heat. So the energy that a reaction gives off is just the products minus the reactants. And again, we will use this formula many times, so don't screw it up. It's products minus reactants. Now, here's an example of it. Consider the equation for the production of water. We have the delta H being negative 483.6 kilojoules. Again, joule is the unit of energy, and it's a kilojoule because it's 1,000 regular joules. And the change in the energy is negative, which means that it's going to produce heat. So when hydrogen and oxygen react together, it produces 483.6 kilojoules of heat, and that's released, and it's, again, exothermic. Now these equations where you see the delta H of a reaction are called thermochemical equations. Thermo meaning heat, chemical meaning it's a chemical change. Now we have enthalpy of reactions being defined as an extensive property. Now the opposite of extensive is intensive. An extensive property depends on how much of the substance you have. An intensive property doesn't matter how much of the substance you have. So density, for example, is an intensive property. So if you have a small piece of gold or a large piece of gold, the density of gold will still be the same. An extensive property means it depends on how much you have. So mass is an extensive property because if you have a small piece of gold, the mass would be different than a large piece of gold. So that's extensive and intensive properties. And enthalpy is extensive, which means if we were to have a chemical reaction, as shown on the screen, with a delta H of negative 802 kilojoules, and we were to double that reaction, well, you would double the amount of heat that's given off. Now, if you reverse the reaction, it's going to change the sign. So instead of doing products minus reactants giving you a negative number, you would do reactants minus products, and you would basically get a positive number. So if you switch the reaction around, if you reverse it, the sign changes. Now, enthalpy change for a reaction depends on the state of the reactants and the state of the product, so you have to be very careful what you're looking up in one of the tables in the back of the book that we'll talk about later. You have to make sure you're dealing with liquids or gases or solids, because the state does change the delta H. So for example, in our first reaction at the top of the PowerPoint presentation, it says negative 802 kilojoules. That's if you have gaseous water as your product. But if it's liquid water as your product, it's actually going to release more heat. It's negative 890 kilojoules released. So if water vapor is the product, it's only negative 802. But if it's water that's liquid, it's going to release 88 kilojoules more. Now we talk about calorimeters. Calorimeter is a device that measures the heat that's flowing into or out of a chemical reaction. And it measures the change in temperature of the water after the reaction is performed, and we do a lab with this, so it'll make a lot of sense to the students after they're finished with the lab. The cheapest way to make a calorimeter is just by stacking a couple styrofoam cups on each other and sticking a thermometer in it, and you have a glass stirring rod in there too. It also has a cork stopper just so the heat doesn't escape the top. That's a calorimeter, and basically what you're going to be doing with the calorimeter is measuring the change in temperature of the chemical reaction that occurs inside the styrofoam cups. Now there's another one called a bomb calorimeter. The one that's on the left, the one with the cork and the cups, that's under constant pressure because it's basically an open container. It's not sealed. The one on the right is called a bomb calorimeter, and that's measuring the amount of heat at a constant volume. So the pressure inside would actually increase because it's a closed container if it's going to produce gases or something like that. You can see in the bomb calorimeter there's a positive and negative terminal, so it produces a lot of electricity to get the sample to catch on fire or whatnot. There's a place so oxygen can go in there, but anyway, you basically burn a substance and it gives off heat. The water's stirred around, so it kind of makes the temperature nice and even, and then the thermometer will go up or down. You know, obviously if you're burning it, it's going to go up, but there are some reactions that are endothermic, so the temperature would actually decrease. So basically a calorimeter is a container where you can measure the change in the temperature of a chemical reaction. Now on the next page we have some more definitions. We're going to measure heat of a reaction, and this time we're going to use the letter Q. So we're kind of going back and forth from the letter H to the letter Q. I hope that doesn't confuse the heck out of you. We have the definition of heat capacity, molar heat capacity, and specific heat. So I'll have them all three on the screen and I can talk to you about them. So heat capacity is the amount of energy required to raise the temperature of an object just by 1 degree Celsius. So if you had a block of metal and you wanted to change its temperature from 30 degrees Celsius to 31 degrees Celsius, the amount of heat that was needed to change its temperature is called the heat capacity. So it's very inspecific about how much stuff you got. The molar heat capacity specifies that you're dealing with 1 mole of the substance and you're changing its temperature by 1 degree, or by whatever the temperature is. So molar heat capacity has the symbol of capital C, and the little p means that it's at constant pressure. And you just have the formula delta H over delta T. So it's the change in the heat over the change in the temperature. So it's the heat that is added to the object to change its temperature a certain number of degrees. So if you were looking at units, it would be like joules per degree Celsius or kilojoules per degree Celsius. It doesn't really matter if you're in Celsius or Kelvin, because the change in the temperature in Celsius or the change in the temperature of Kelvin would be the same. Now specific heat, just like molar heat capacity, the specific heat capacity tells you specifically how much substance you're dealing with. Molar heat capacity deals with 1 mole. Specific heat deals with only 1 gram of the substance. And this is the main formula that we're going to be using when you calculate how much heat is given off by an object. You take the grams of the substance, which is the mass, the M, and then you multiply that by the specific heat, and then you multiply that by how much the temperature changes. So the formula is Q equals MC delta T. Some students call it MCAT because it kind of looks like the letter M, and then the C and the delta kind of looks like an A, so they call it MCAT. But anyway, it's Q equals MC delta T, and we're going to do a practice problem using it on the next page. Now, if the specific heat of water, a constant that you're going to be given a lot in homework problems and on tests and stuff, the specific heat of water is 1 calorie per gram degree Celsius or 4.184 joules per gram degree Celsius. And what that means is that if you wanted to raise 1 gram of if you wanted to raise the temperature of 1 gram of water 1 degree Celsius, you're going to have to add 1 calorie of heat. Or if you want to raise the temperature of 1 gram of water 1 degree Celsius, you're going to have to add 4.184 joules of heat. So that's what the specific heat capacity of water refers to. The units are kind of weird, but it makes everything work out. Now here's your practice problem. It says how many joules of heat will raise the temperature of exactly 50 grams of water from 25 degrees Celsius to 75 degrees Celsius. So we know we're going to have to put in the heat, and we just multiply the Q times we multiply the M times the C times the delta T. Since it wants the units of joules, we're going to use 4.18. I just rounded it to 3 sig figs. You end up getting 10,450 joules, and that's how much heat would have to go into the system. Now, if you wanted to calculate the molar heat capacity for water, what you can do is you can take the conversion factor of 4.18 joules per gram degree Celsius times the molar mass, and you will get the units of joules per mole degree Celsius. And I summarized it in a formula: big C, which is molar heat capacity, equals little c, the specific heat, times M, which is the molar mass or the molecular weight of water. So big C equals little c times big M. That formula is not on your AP equation sheet that I know of. Now we talk about Hess's law, which is a pretty important concept we use a lot throughout the year. It's introduced in this chapter, but again, it's used all over the place. If a reaction is carried out in a series of steps, the delta H for the reaction, the total delta H for the entire reaction, is just equal to the sum of the delta H's for each step. Now the total change in enthalpy is independent of the number of steps, so this works with a 1-step reaction to a 10-step reaction or whatever. And the delta H is also independent of the path. Since delta H is a state function, it doesn't really matter the path that you get from the beginning of the reaction to the end. As long as you are measuring the delta H, everything works out. So here's a small example, and we do some practice problems during class, and there's some assigned for homework too. So here's the one in the notes. We have methane being burned. CH4 gas plus 2 oxygen molecules, that's obviously a gas, yields a carbon dioxide molecule and 2 waters. And water is a gas in this example. We're going to add to that a reaction where gaseous water is condensed into the liquid, and we recognize these numbers from the previous slides. We have negative 802 kilojoules being released for the first reaction. We have negative 88 kilojoules being released for the second reaction. When you add these up, it's kind of like math class, where if you have something on the right side of a math equation and you have the same substance on the left side, you can cross it out. So if you add these two reactions together, what you will end up with is a net equation where methane is burned with oxygen and you're producing liquid water, and when you add the delta H's together, You have negative 802 plus a negative 88 gives you a total delta H of negative 890 kilojoules. And the reason we have Hess's law is because it's a very useful way to calculate the energy changes that are often difficult to measure. For example, if you were to burn methane and oxygen, you're probably not going to get liquid water. You're going to get water vapor because it's so hot. So if you wanted to calculate the energy released if it were to produce liquid water, this would be a great way to do it. You could form the gaseous water and then find the reaction for gaseous water to liquid water, and you would get the negative 88 kilojoules added to the negative 802 for a grand total of negative 890. Now we're talking about enthalpies of formation. The definition is as follows. If a compound is formed from its elements, from its constituent elements, then the enthalpy change for the reaction is called the enthalpy of formation, and so it's called delta H sub F, or delta HF. So if you were to make carbon dioxide gas from its pure elements carbon, which is a solid, and oxygen, which is naturally O2 as a gas, you would have the delta H of formation of negative 393.5 kilojoules, and again that's exothermic. Now standard state are standard conditions, and they refer to these particular pressures and temperatures. Standard pressure is 1, but the standard state conditions for reactions is actually 25 degrees Celsius. It's not 0 degrees Celsius, it's 25. So we will assume that all the reactions that we do, the reactions and products, are both at 25 degrees Celsius unless they otherwise state that, but I don't know of any problems that are not done at 25 degrees Celsius. There's a bunch of numbers in the back of your book for delta H of formations, and they're basically all at 25 degrees Celsius. Now the standard enthalpy is called delta H with a little 0 up in the corner. It looks like a degree sign. It's actually pronounced naught, N-A-U-G-H-T, so it's delta H naught. Some kids think it's not N-O-T, but it's actually naught, like 0 and nothing. So anyway, it's delta H naught. That's the enthalpy measured when everything's in its standard state. So if you see the little 0 in the corner, the little degree sign, that means it's at 1 atmosphere and at 25 degrees Celsius. So we combine the two definitions. We have the enthalpy of formation, which has the little F, and we have the standard states, which has the little degree sign. So the delta H naught sub F is the enthalpy change for the formation, and this is very, very important because it's on your quiz or your test, and kids always miss it. You're only going to produce 1 mole of the compound, and all the substances have to be in their standard state. So your product has to be 1 mole for it to be the delta H naught F. You cannot produce 2 moles, you can't produce a half a mole. It has to be producing 1 mole of the compound, 1 mole of the product in its standard state. And I'll define standard state on the next page. If there's more than one standard state for a substance, the more stable one is used. So a good example is carbon. Carbon has 3 allotropes. We know there's carbon that's graphite, and there's carbon that's diamond, and there's carbon that's buckyball, which is the C60. Well, the most stable one is carbon that's graphite. So when you ever have a reaction with carbon, if you look up the value of the delta H naught sub F, you're going to use the one that's for graphite unless otherwise told. Now by definition, the standard enthalpy of formation of the most stable form of the element is 0. Now why would that be true? Well, because there's no formation reaction needed when the element's already in its standard state. So you just dig up carbon, and it's naturally going to be carbon that's graphite. If you want to change it to diamond, you're going to have a delta H for the reaction going from graphite to diamond. But just graphite, since it's the more stable one, it just has a delta H of formation of 0. So I put 3 examples down. You have the delta H of formation naught, that's your standard enthalpy of formation for graphite, is 0. Oxygen is naturally O2 as a gas, that would be 0. And here's another example. Bromine is naturally a liquid, and it's Br2. That's its standard state, so it's also 0. Now here's the formula that's shown on your AP equation sheet, I believe. It basically says you're going to take the sum of all the delta H naught F's, that's the standard enthalpy of formation of all the products, minus the sum of all the standard enthalpy formations of the reactants to get the total delta H naught of a reaction. Whew. Now the letter N and the letter M refer to the number of moles that are in the chemical equation. So we're going to do a practice problem so we get used to doing products minus reactants just like we did before, but we're going to use the standard enthalpy of formation values that are shown in the back of your book. So we're going to use Hess's law to calculate the delta H naught of the reaction. That means the standard enthalpy of this reaction. We're going to take propane, which is C3H8, burn it, and we're going to produce carbon dioxide gas and liquid water. So we're going to form each of these substances from their pure elements. So we're going to form carbon dioxide from its pure elements, and we're going to form water from its pure elements. Now, when you look up in the back of the book, the delta H, that's producing 1 mole. But because it's an extensive property, if you're producing 3 moles of the carbon dioxide, we're going to have to actually look up the delta H of formation of carbon dioxide gas and triple it. And we'll also look up the delta H of formation of liquid water and quadruple it because we're producing 4 moles. So if you were to add up these reactions, you would end up getting 3 CO2s being formed and 4 H2Os being formed. The next part, it just says that you don't have to worry about the delta H of formation of oxygen because it's a pure element in its standard state. The delta H formation for propane is again reacting carbon with hydrogen, and that's the standard conditions of carbon is a solid and the standard conditions of hydrogen is H2 gas. And that delta H value, that again you can look up in the back of the book in one of the tables, is on page 177, and also it's in, as I mentioned earlier, it's in the table, but I don't remember the page number. But we can look up the values of all the delta H naught formations of the products. We're going to add those together, and we're going to subtract the delta H of formation of the reactant, which is just CH3, or C3H8, I'm sorry. So we just sum all the delta H's, look them up in the back, and plug and chug. So we have tripled the value for carbon dioxide, we've quadrupled the value for the water, and we're going to subtract out the value we look up for propane, the C3H8 in the back of the book. So you're actually going to be minusing a negative 103.85 kilojoules. And all the units are kilojoules after you multiply by the 3 moles or the 4 moles. So you end up with a delta H naught of the reaction of negative 200 or 2,220 kilojoules. Finally, on the last slide we have the heat of fusion and the heat of vaporization. The molar heat of fusion, called delta H sub FUS, is the amount of energy required to take 1 mole of a solid and you're going to change it to liquid. So basically you're melting it. The delta H fusion, or the delta H to melt ice, is 6.01 kilojoules, and that would be 1 mole of ice. So the heat of fusion is usually greater for ionic solids, so if you're trying to melt table salt, it's going to be a heck of a lot higher than if you're melting molecular solids like water, because the ionic solid bonds are a lot stronger, and so when you're trying to break those ionic bonds to liquefy salt, it's going to be a lot tougher to do. For ice to water, I already wrote that down at 6.01 kilojoules per mole. The molar heat of vaporization is basically taking the liquid and turning it into a gaseous state. So the example I show is taking liquid water and turning it into water vapor. And you can see the number's a lot bigger. It's 40.67 kilojoules. And notice that both of these values going from solid to liquid or liquid to gas, they're positive numbers because you have to add in the heat. So it's an endothermic reaction. For water to steam, it's 40.67 kilojoules per mole. I put in the kilojoule per mole unit to stress that these are mainly used as conversion factors. So when you're doing textbook problems and you're trying to boil water or melt ice and things like that, they'll usually tell you how many grams there are. You can convert grams to moles and then just multiply by this conversion factor to see how many kilojoules are needed to complete that physical change. And that's basically the notes for this chapter, and we do a lot of practice problems and even a lab. So we'll be stressing the products minus reactants for the rest of the year for delta H's.